Hello and welcome to the third video on kinematics. This time we'll see how ideas and equations covered in the previous videos can be applied to projectiles simultaneously moving in vertical and horizontal directions. We'll also discuss how a free-falling body can be practically used to determine the value of the free fall acceleration on our planet. We will start by looking once again at an example of a body in free fall. As you can see, an object in free fall is moving vertically down towards the center of the Earth with constant acceleration, which is called the free fall acceleration, and on our planet is equal to 9.81 meters per second squared. We'll come back to this value later in this video. But what would happen if instead of just dropping an object, we would fire it with some horizontal initial velocity? Would the time it takes for the body to reach the ground increase because the object is moving horizontally in addition to vertical motion? Let's have a look. As you can see, the fact that the object is moving with a horizontal velocity does not affect its vertical motion. It still takes the same time to reach the ground despite moving in the horizontal direction. Please note that if air resistance is negligible, horizontal velocity does not change throughout the motion. Since horizontal motion does not affect the vertical motion, we can conclude that horizontal and vertical motions are independent from each other and can be treated separately. In vertical direction, the object is moving with uniformly accelerated motion, and in the horizontal direction, it's moving with a uniform motion at constant speed. This is due to the fact that the only force acting on the object is gravity, which acts vertically, and there is no horizontal force if air resistance is negligible. We'll further explore how forces affect motion in the next topic called dynamics. Let's try to calculate the range of a projectile fired horizontally from a known height h with an initial velocity vx. Range is equal to the magnitude of the horizontal change of displacement. As we are trying to calculate the horizontal change of displacement, we need to consider horizontal motion of our projectile, which is just a uniform, constant speed motion. So to calculate the range, we have to multiply the magnitude of the initial velocity and the time it takes to get to the final position. We have assumed that we know the initial velocity, so to calculate the range, we just need to find time. While projectile is moving horizontally, it is also moving in the vertical direction. These two motions are independent but are happening at the same time. So all we need to do is to find how long it takes to just fall down from the initial height h. Falling objects move with uniformly accelerated motion, so we can use this equation, where h represents the distance the object will travel in the vertical direction. Initially, the projectile was fired horizontally, so its vertical initial velocity was 0. Rearranging this equation yields this. We managed to find the time it takes to fall from the initial height, which is also the time it takes this projectile to travel to the final position. Replacing time in our first equation with the expression we have just arrived gives us the final equation that we could use to calculate the range of a projectile fired horizontally from a known height with known initial velocity. Let's now talk about a projectile fired with an initial velocity at an angle. This short clip illustrates the situation. The velocity of the projectile can be represented by two perpendicular components showing horizontal and vertical velocities. We can see again that vertically our projectile is moving in exactly the same way as an object fired vertically up with the same initial vertical velocity. Once again, horizontal and vertical motions do not affect each other and can be treated separately. Let's see if we can find a way to calculate the maximum height that the projectile can reach. We'll assume that we know the initial velocity and the angle at which the projectile was fired. Since height is measured in vertical direction, we can start by considering the vertical motion, which, as we have previously discussed, is a uniformly accelerated motion. Since we are dealing with a uniformly accelerated motion, we can apply this formula, where h represents the height or vertical change of displacement, u represents the initial vertical velocity, and v represents the final vertical velocity. At the highest point, vertical velocity becomes 0. Initial vertical velocity is equal to the vertical component of the initial velocity, and acceleration is downwards, so should be treated as negative. Initial vertical velocity can be expressed as v sine theta. Plugging our assumptions into the equation, we get this, and rearranging gives us the final equation, which we can use to calculate the maximum height a projectile fired at a known angle and with a known initial velocity will reach. At what angle a projectile should be fired in order to reach the maximum height for a given initial velocity? Well, if the only thing we can change is the angle, we need to think at what angle sine squared theta will have the maximum possible value. Sine function reaches its maximum at 90 degrees, so not very surprisingly, we'd have to fire our projectile vertically up if our aim was to get it to the maximum possible height. This maximum height could be calculated with this formula. Let's once again assume that we have a projectile fired with a known initial velocity at a known angle. This time we'll try to find the maximum horizontal change of displacement, which we can call range. Initial velocity can be represented by two perpendicular components, vertical velocity Vx and horizontal velocity Vy. Since our task is to calculate range, which is measured horizontally, we'll start by considering horizontal motion. As you can see in this clip, horizontal motion of a projectile is uniform, so we can use this formula. Knowing the initial velocity and the angle, we can easily find the horizontal component using this formula. Now we only need to find the time it takes the projectile to reach the final point. In a very similar way to the previous example, we can use the fact that while the projectile is moving in the horizontal direction, it is also simultaneously moving in the vertical direction. Vertical motion is uniformly accelerated, so we can start by looking at this equation. Assuming that the positive direction is up, vertically the initial velocity is Vy. Projectile will be falling down just before hitting the ground, so final vertical velocity is minus Vy. Acceleration is downward, so a equals to negative g. Plugging these values into the equation gives us this. Rearranging and replacing Vy with v sine theta gives us the final formula for time. Now we can replace Vx and t, which gives us this expression. We can use this trigonometric identity, which you have probably covered in mathematics, to find the final formula, which can be used to calculate the range of a projectile fired at a known angle with known initial velocity. You don't necessarily need to memorize this formula, but I hope that the last two examples will help you to understand how equations of motion and independence of vertical and horizontal motion can be applied to calculate various things. What initial angle will result in maximal range? Range is maximal when sine 2 theta is maximal, which means that 2 theta must be equal to 90 degrees, so for maximal range, theta should be 45 degrees. Quite a few times in this topic we have used 9.81 as the value for the free fall acceleration. Could we apply equations of motion to design an experiment that would allow us to confirm that free fall acceleration is truly 9.81? Let's start by assuming that free fall is a uniformly accelerated motion. If that's the case, we should be allowed to use this formula, which is a formula for distance in uniformly accelerated motion. In our case, distance is equal to the height h from which the object was dropped, and acceleration is assumed to be constant and equal to g. Since we can drop the object, we can assume that the initial speed u is 0, and we get this final formula. We could just drop an object once, measure the height of the drop, measure the time it takes to fall, plug results into our formula and calculate the value of g. Unfortunately, using just one value for height and time is not the best practice. What if there was a random error in any of our measurements? What if g is not actually constant and is different for different drop heights? To address these problems, we can take a series of measurements of time for different drop heights, which is the correct scientific approach. Height of drop h will be the independent variable that we will be changing, and time of fall t will be the dependent variable that we will measure. What are we actually going to drop? To minimize the effects of air resistance and to get as close to free fall as possible, we should use a small dense object. Steel ball bearing would be just perfect for the job. To make sure that the test is fair, we should keep the diameter of the ball and the density of the ball constant. We can do that by simply using the same ball throughout the practical. After measuring time t, we can also calculate the value of t squared. Why would we do that? Notice that if the fall of our ball is really free and is truly an example of a uniformly accelerated motion with constant acceleration g, the graph of h against t squared should be a straight line. After plotting the best fit line, we can calculate its gradient, and we can use the gradient to calculate the value of the free fall acceleration. How are we actually going to measure things in this experiment? Height of drop can be measured with the meter rule. Please note that the height should be measured from the bottom of the ball. Electromagnet will be responsible for releasing the ball, and stopwatch triggered by a trapdoor can be used to measure the time. Time measurements for each height should be repeated to further reduce random errors. There is already an excellent video which shows this equipment in action. Please check it out, link is in the description. After measuring time 3 times for each height, all results are recorded in a table. The average time and the average time squared is then calculated, and these 2 columns are used to plot the graph. In the next step, gradient of the graph is calculated. Now we can finally calculate the value of the free fall acceleration. To get our final result, we just need to multiply our gradient by 2. Thank you for watching, and I will see you in the next Easy Physics video.